Bismillah ar-Rahman ar-Rahim. Welcome everybody. We are going to start with the first presentation that will be given by Dr. Adil Haddad. Dr. Adil Haddad is a research scientist and program manager for wastewater treatment and reclamation technologies, program in the Water Research Center at Kuwait Institute for Scientific Research. He graduated from Kuwait University in 1985. He got his MSc in groundwater resources management. He obtained his PhD in wastewater treatment from the University of Strathclyde in UK in 2000. Dr. Adil Haddad has participated in several surface water, groundwater, domestic and industrial wastewater projects. He has more than 20 years experience in the field of geology, chemistry, microbiology, water contamination, and treatment technologies. He has more than 50 publications in refereed journals and international conferences, 4 books, 100 technical and final projects reports related to water resources management. Dr. Adil, floor is yours, please.
Can I ask for the presentation? Presentation? Assalamu alaikum. This presentation will be focused about wastewater industrial database for nitrogen Shu'aiba area in Kuwait. I'm presenting this paper also on behalf of my colleagues, Mr. Muhammad Al-Muntasir, also Mr. Hussein Abdullah, and Mr. Abdullah Al-Ma'touk, and Dr. Abdullah Abu Sam. This paper is presented from Kuwait Institute for Scientific Research. I will try to give a brief description for the problem of the industry wastewater sector. Then I will discuss the objective of the study, the methodology that we used during the study, result that we got, and the conclusion and recommendation that we suggest at the end. Kuwait mostly depends on the need for domestic or commercial or even industrial wastewater on the desalination, the potable water which is produced from desalination plant. The program for integrated water resources management scheme, which includes all the aspects for wastewater treatment, reuse, disposal, energy generation, resource recovery, we don't have it in Kuwait. So one of the major sectors involved in such a scheme, the industrial wastewater, which include petroleum and non-petroleum factories. How much wastewater these factories are producing and what kind of the treatment they are using there, and characteristic of wastewater is produced from each group of factories for each industrial area. So we need here to build up a database which include, using ArcGIS, which includes all data of the factory and the wastewater which is produced. Is it from freshwater and the wastewater which is generated from each factory? And this database, we started to build up for it. So the objective of the study was to determine the quality and quantity of 17 petroleum industrial wastewater from different sources in Shu'aiba area in Kuwait over 1 year study period through using the GIS system. The task methodology we divided to 4 parts: mobilization and survey of industries, industrial wastewater sampling and laboratory analysis, preparation of database and data entry, then the results and discussions. We did survey for the industries and also all the activities which needed, including getting the chemicals, consumables, which is required, plus the field equipment, which we need to also do on-site measurements. All these are purchased. Also, field survey in 2 languages, Arabic, English, were distributed to the owners of the factories, especially for sampling, field measurement activities, and getting some data also from these factories. The industrial areas in Kuwait, mostly they are set in 3 areas: Kuwait City, Sabhan, and Shu'aiba area. Shu'aiba industrial area represents factories of petroleum wastewater origin, while the other 2 locations represent non-petroleum wastewater origin. This paper will focus mostly on Shu'aiba factories. So you can see the yellow circles in the north. This is for Kuwait City. In the middle, Sabhan. In the south, down the yellow square is for factories of Shu'aiba industry area. We did survey, Arabic-English survey for each factory. We tried to put all the information of the factory. This is just part of the question we ask the staff of the factory to answer it. Yani, how much fresh water they are using for each factory, how much wastewater is generated, also what kind of treatment if they are using, what are producing in each factory, how many stages, production lines. There is a lot of questions. This is just part of these questions or survey. This is long survey, just I'm cutting few questions for it. Is this water which is out from the factory are monitored by Kuwait EPA or PI, Public Authority for Industry, who gives the permission for the construction of these factories? So there is a lot of questions in this survey. And based on this survey, we move to the next tasks. So after we collected the data from these surveys, we tried now to make a plan for wastewater sampling and analysis associated with also on-site field measurements. We collected, or we got approval from 41 factory total. 17 factories is from Shu'aiba, 10 factories from Kuwait City, 14 factories from Sabhan area. Also, field measurements were carried out for all sites, including the temperature of the wastewater. Here we are speaking about raw wastewater. Temperature, pH, electrical conductivity, dissolved oxygen, and oxidation reduction potential parameters for each factory. We measure these parameters. And the collected sample from this factory, it was analyzed for full analysis for physical, chemical, organic, biological, bacterial, viral, toxicity. There is a lot of analysis part there. And these analyses were carried out according to the standard method for examination of water and wastewater, APHA 2017. And these parameters were analyzed in Water Research Center laboratories in QEERI, Kuwait Institute for Scientific Research. This is just, I'm trying to pass these slides, photos for collection of the raw wastewaters, the field measurements from the sites, plus also there is measurement in the lab also. This is some of the equipment which you used during the analysis. I'm trying to pause for the time. So all factories from which wastewater samples are being collected were coded, and we started to establish Excel spreadsheet database was prepared, and all the field and laboratory results for each factory, for each industrial area were tabulated. After that, ArcGIS software was used to convert the Excel database to GIS database, and from these GIS database, we generate a lot of maps for each parameters and for each industrial area to see the distribution of contaminant of the wastewater for each area. This is the factories which we collect samples from it, and we did field measurements, and their coordinates, northeast coordinates. We need these coordinates for mapping. This is the location map for all these 17 factories during the study. This graph shows the quantities of freshwater and wastewater which is generated from the factories of Shu'aibah area. On average, these factories, they are based on the obtained data. These factories, they're producing around 63 meter cube per week. Except 3 factories, the pH values for the raw wastewater are within Kuwait EPA limits, which is between 6.5 to 8.5. So we don't have, with most of these factories, there's no problem with the pH. Also for the electroconductivity values, we found that all these factories, if you see that the maximum EC, it's reaching, and except one factory, it's 2,000 conductivity microsiemens per centimeter. It means they are below 10,000 milligram per liter salinity. It means all they are brackish water except one reading. It's their origin is potable water, so when you got the contaminant, sure, it will go to brackish class there. The ORP, oxidation reduction potential for the wastewater, you can see that all these values, they are below, in the negative values, below 0. It means they are in reduced environments, okay? Except one value for Kuwait Gypsum Manufacturing Company, which shows oxidation. I'm trying to pass some of these. Now, everyone knows that nitrogen is very important for plant growth. It's used as fertilizer. So this paper is targeting the total nitrogen in the raw wastewater for these factories. Kuwait EPA set a value of 65 milligram per liter as a maximum limit to use this water for irrigation. You can see, except Kuwait Lubricant Oil Company, all these values, they are below the value set by Kuwait EPA. It means, with respect to total nitrogen, no need to treat raw wastewater from these factories, which we selected and studied in this study. This is the distribution of this is GIS map for minimum values of total nitrogen. The red rectangle is here, you can see it for Sabhan, but Shu'aibah is the blue. You can see within the blue, the lesion, the concentrations, mostly are in green color, okay, because they are minimum values. If you go to the averages, you can see the yellow color is coming with the green colors also, with slightly the concentration is moving up for total nitrogen. When you go to maximum values for the total nitrogen, again, the orange and the yellow and the green colors is appearing here with a slightly increasing the concentration of the total nitrogen. The message here for total nitrogen that we don't have any problem with respect to this fertilizer. It can be used safely without even any sort of a treatment. Just to conclude, so from this database study, all the field and laboratory results indicated that total nitrogen, their concentration in the wastewater are meeting Kuwait EPA irrigating water standard, except those values of total nitrogen, which is above 65 milligram per liter. It's only for one factory, Kuwait Lubricant Oil Company. And the obtained field data also suggests that only a few industries use on-site wastewater treatment system there for these factories. Now, continuation of this database, as a request from Kuwait Foundation for Advanced Science, they asked us to send the final report of this study to EPA and PI to continue the measurement and updating the database, especially the PI, this authority is responsible to give the permission for the factories to be established there. Also, on-site treatment systems such as pH buffer tanks, sand and carbon filtration, disinfection unit should be installed to treat industrial wastewater, especially for a group of factories. For example, if you have soft drinks of different brands, let's say Pepsi or other types of, so we can make one type of treatment unit to treat these similar source of water. We can use this treatment on site to deal with it. Here, unfortunately, most of these factories, they don't have one drainage system. They have combined drainage system. The industrial wastewater is combined with domestic wastewater. This is the reason sometimes you may find bacteria and contamination in there. Some factories, no, they have separate. They don't have, I mean, the industrial is separate from the sewage lines. There are less contamination for these factories. At the end, I thank you for your presentation.
Thank you very much, Dr. Khaled, for interesting presentation and valuable information given in the presentation.
A few questions.
Okay, Dr. Adel is in a hurry. If anyone has any question, we can get just 2 questions because he has a flight. I think he has to leave. Any question to Dr. Adel? Okay, thank you, Doctor. No questions. Okay, next presentation will be given by Dr. Khaled Bani Milham. Actually, Dr. Khaled is a research associate professor in the Center of Advanced Materials at Qatar University. He graduated from Jordan University of Science and Technology with BSc and MSc in Chemical Engineering in 1995 and 1998 respectively. Dr. Khaled received his PhD in civil engineering, in civil and environmental engineering from Concordia University, Montreal, Canada in 2008. Before joining Qatar University, Dr. Khalid worked at Hashemiyat University in Jordan in the Department of Water Management and Environment from 2012 to 2022 as assistant and associate professor. He also worked at the American University in Cairo from February 2010 to August 2012 as a postdoctoral research on a collaborative project funded by the King Abdullah University of Science and Technology. Dr. Khalid published more than 40 papers in high-ranked journals. His research interests focus on developing innovative solutions addressing issues across all relevant environmental media, specifically on wastewater treatment and reclamation and water desalination. Dr. Khalid, the floor is yours.
شكرا دكتور يعطيك العافية. السلام عليكم جميعا. بداية اسمحوا لي أن أتقدم بالشكر للقائمين على هذا المؤتمر ممثلة بالمؤسسة العامة القطرية للكهرماء وجمعية العلوم وتقنية المياه الخليج العربي. I will mix my language between Arabic and English to deliver more information from this session actually. I am going to talk about a novel technology which was developed actually at Concordia University in 2008. This technology called submerged membrane bioreactor. In this presentation, I am going to present introduction for the current facilities for wastewater treatment plants in general, and the circumstances that face these technologies, and what was the motivation in Concordia University to develop this kind of technology, and what was the research methodology we have followed in our research lab, and the application of submerged membrane electrobioreactor, and the limitation for this technology. Finally, I will deliver some recommendation for the interested researchers here in Qatar or in the Gulf area, which can make maybe collaboration in the future. This figure actually shows the current facilities for wastewater treatment, which consists of from three stages actually: primary treatment, secondary treatment, and tertiary treatment. We have some limitation or some circumstances in applying this technology actually. For example, if we applied only primary treatment, we cannot reach all the accepted standards for this treatment. If we applied secondary treatment, we need we produce high amount of sludge, and this is a challenge for all wastewater treatment plants in the world. Also, we need more space for the secondary treatment, and sometimes they doesn't reach the acceptable standard in the treatment in terms of nutrients, fouling, nitrogen, and phosphorus. And even the tertiary treatment need high operating cost. And the sludge, as I said, consists a major problem in wastewater treatment plant facilities, which accounts about 60% of the total cost in water treatment in dealing this issue. So now the general trend to decrease the amount of sludge disposed to the environment, and also reduce the necessity for the advanced treatment in all facilities in the wastewater treatment plant. So still, we have also problem in the clarifier that's used to make separation of the effluent produced from the bioreactor. From this issues, the idea of developing the current wastewater treatment plant comes in 1969 from the researchers called Smith. he suggests to replace the secondary clarifier by a membrane unit. And we produced a new technology, which is called membrane bioreactor, MBR now. It's now very famous technology. We have two configurations of this technology, the external one, which started in, as I said, in 1969. And the second one was the submerged membrane bioreactor, invented by Yamamoto in 1989. He put the module of the membrane inside the bioreactor. By this way, they reduce the land requirement almost about 50%. This is a comparison between the two configurations. As you see here in the slide, the external can give high flux, but need more energy and need more space, while the submerged need less cost, but the flux should be less in comparison with the external facilities, and need less membrane area. This is the concept, actually, of the membrane bioreactor. This is an interaction between biological processes and membrane filtration processes. However, we have, as you know, in any membrane technology, the fouling is still considered a major issue in applying this technology. In conclusion, the membrane fouling will reduce few of circumstances, such as decreasing the permeative flux, decreasing the efficiency, and increasing the maintenance, and increasing the operating cost. The current strategy for anti-fouling can be done by washing the membrane, supplying air near the membrane surface, optimizing the operating conditions, improving the wastewater characteristics. But in this case, we need to add more chemicals, and we have to use more absorptive material. The impact of these strategies actually increasing the operating cost and producing high amount of sludge. So we are looking for developed another strategy. From this circumstances, our idea of the research is coming by integrating three main technologies in one facility: electrokinetics process, membrane filtration, and biological process. And this was the first innovation was done at Concordia University in 2010, which as I said, connect three technologies in one facilities: biological process, electrokinetics, membrane filtration. So our target was how we can design a best facility for this technology, and what are the best operating parameters, and how we can performance this technology in terms of effluent quality, and how the degree of reducing the fouling by applying this technology. This technology, as you said here, interact three main processes together, and we call this process is a submerged membrane electrobioreactor. So we integrate the bioreactor with microfiltration, with ultrafiltration, and applying inside the sludge itself, inside the bioreactor, we applied the electrokinetics on the sludge. You know, the sludge contains microorganisms, and these microorganisms are very sensitive for applying the direct current. We don't need to die or to kill this microorganism, because we need to keep them survive to do the biological treatment. We have some problem here when we designed our technology in terms of what are the suitable kinds of material for electrodes. Also, we need to decrease the electrical current efficiency, as I said, because we don't need to affect the microorganism growth. And we need to keep a direct current field between the electrodes identical in all directions. And finally, the electrode assembly should not interfere the feed and flow toward the membrane during the operation. Also, we have to keep the undistributed circulation of the air in the bioreactor. We have circumstances or constraints also on the electrical parameters. we don't need to apply electrical kinetics that can maybe affect the microbial activity. And we have to apply an accurate current for the DC. And we have to choose the best operating mode in terms of the applied direct current. And the electrical field cannot affect the longevity of the membrane. We need also to keep the life of the membrane itself. This figure actually summarizes our invitation. Figure B is all the facilities included in our technology. Figure C is the top view of the membrane. We have two zones. Zone 1, in which the biological treatment occurs, and zone 2 is the filtration process occurs in the membrane filtration, which was the ultrafiltration module.
3 minutes left.
I have 5 slides. Okay. This is the electrokinetics process occur inside the membrane itself. We have ionic reaction. The metal dissolved and gives us the ions. On the cathode, water reduced to OH plus H2 gas, and other reaction. Here, if we applied iron as electrode material, we have these equations, chemical equations, and we get precipitation for example, for phosphorus, reduce the amount of phosphorus almost more than 99%. By the way, we get many advantages of applying our technology, such as a small footprint, no chemicals needed for this technology. We reduce the operating cost by reducing the requirement of aeration, improving sludge dewatering conditions, and the design of our technology can find application for different various types of wastewater, including sewage, without even extensive pre-treatment. Such solution is required by small municipalities, such as can we use it for mining areas, agriculture facilities, military bases, and different regions. Finally, such this compound, this technology can be used as a mobile unit and can be driven by solar energy, which is suitable here in the Gulf area. However, we face some circumstances and limitations during the applying of our technology, such as the direct current. We found that DC reduced some activity of the microorganism during the operation, especially the nitrification process. So this is a recommendation for the researchers who are interested in this technology, how we can modify the operation of the process. Also, energy consumption can be a limited factor. However, we don't need high amount of energy, and we can driven our technology by solar energy. As I said, is suitable for Gulf area here. This is some examples of the, after 15 years of invitation, now we have more than 200 publications referred to this technology. This is the most famous found in the literature. All of them increase the fouling or reduce the fouling by more than 50%. Here also another researcher. And also the effluent of the wastewater treatment was very high in terms of COD, phosphorus, nitrogen. Here I am driven some recommendation who are interested in continue on this field. They can continue with these points. We need to apply a biology scale investigation for this technology. Also the impact of some parameters such as the sludge retention time, hydro retention time, still need further investigation. We need to analyze also the cost analysis, and we have to investigate what are the best electrical parameters that should be applied in terms of direct current air gap between the electrodes, and finally the materials of electrodes also very important in this design. Thank you for your attention.
Okay. Thank you very much, Dr. Khaled, for an interesting presentation. The next presentation will be given by Dr. Abdulrahman. Actually, just to introduce Dr. Abdurrahman. Dr. Abdurrahman works at Saudi Irrigation Organization as a research specialist. He attained his BSc and MSc degree in chemistry from King Faisal University. He has a wide experience in water quality control and management and water quality modeling. Also, he has several publications in the field of chemistry and water quality assessment. He worked in Saudi Irrigation Organization as acting head of the test and certificate issuance units. Also, he worked as research specialist, research analyst, laboratory analyst, and laboratory research assistant. Also, he worked in King Faisal University as a laboratory research assistant for 4 months. Okay, Dr. Abdurrahman, floor is yours.
Many thanks for this nice presentation. This is Abdurrahman Al-Ablan, thank you very much. This presentation is entitled Farmers' Attitude Regarding the Reuse of Treated Wastewater for the Agricultural Irrigation. Before I dive into the details of this presentation, I would like to give a brief introduction about the Saudi Irrigation Organization. Saudi Irrigation Organization is a governmental institution that was established in 2018 to replace the Irrigation and Drainage Authority that was previously established in 1971. The SIO is responsible for operating the irrigation and drainage sector in the Kingdom of Saudi Arabia. Although we are under the umbrella shade of MIWA, which is the Ministry of Environment, Water and Agriculture, we have our identity in terms of the execution of the projects as well as collaborating with the stakeholders. The headquarters of the Saudi Irrigation Organization is positioned in Al-Ahsa Oasis, besides having several branches that are distributed in the kingdom. For example, we have a branch in Dawmat al-Jandal, we have another branch in Riyadh and in Medina, Taif, and we are expanding to cover all the Kingdom of Saudi Arabia. As any organization, we have our vision and mission. When it comes to our vision is leading the development and modernization of the irrigation sector in the Kingdom of Saudi Arabia to achieve the economic and environmental sustainability by enhancing the efficiency and preserving natural water resources. While our mission is the development of the irrigation and drainage network to improve the irrigation efficiency while expanding the reuse of treated wastewater as an unconventional water resource, besides using the conventional water resource, which is the groundwater. We have 5 strategic objectives and 5 strategic programs, including resources sustainability, which includes the reuse of treated wastewater, for example, groundwater and dams water. The quality and accessibility, which indicates that we have to ensure that the water quality delivered to the farmer's outlet meet the regulations of the KSA as well as the WHO, as well as the services provided by the Saudi Irrigation Organization has high quality. Social well-being, as well as economic contribution and the awareness of the farmers. When it comes to the strategic programs, we have 5 strategic programs, including the irrigation, water supply and delivery, monitoring and compliance in terms of the water quality and quantity, improving the irrigation sustainability, building the capacity and capability, and on-farm management through the adoption of modern irrigation techniques. The Kingdom of Saudi Arabia, similar to Qatar, we suffer from water scarcity. We suffer from low rain precipitation. So the agricultural sector depending mainly on the groundwater, as the agricultural sector worldwide consumes about 70% of the total water demand. In the Kingdom of Saudi Arabia, according to National Water Strategy, we consume about 84%, which is very high, where 90 of that number is coming from unsustainable water resource, which is the groundwater. So we have unsustainable water resource. We have a deterioration in the water quality, as in some wells, in some groundwater reaches 7,000 ppm. So we have to find other water resources. That's why we have to shift towards the use of a treated wastewater, and we have to adopt it actually. Even after adopting this water resource, we still have limited use of the treated wastewater, as we have not exceeded 22%. So in order to maximize the reuse of treated wastewater, we have to build, to expand the infrastructure and build STBs to achieve 75% by the end of 2030. There are some concerns related to the reuse of treated wastewater, including the expected chemical contaminants as well as microbial contaminants. So we have to enhance the treated wastewater quality to ensure that the treated wastewater quality delivered to the farmer's outlet has no impact or no any side effect. Also, we have another challenge related to the lack of awareness, as some people think that they have some belief that the treated wastewater cannot be used, or they have some actually cultural beliefs about the treated wastewater, as they used to rely on the groundwater for making ablution, for example, which is not in the case of the treated wastewater. So we have to raise the awareness through different methods, including questionnaires, expansion programs, and so on. This objective focuses on assessing the awareness of a perception of the farmers regarding the reuse of treated wastewater, identifying concerns and barriers why some farmers don't want to adopt the treated wastewater, evaluating the information and policies awareness, examining the demographic influences, as well as developing sustainable recommendations. The methodology adopted for this study, the questionnaires, where we collected several questions information about the farmers, the social and economic characteristics, the irrigation system adopted by the farmers themselves, and we conducted the study in several regions, in Al-Ahsa, in Al-Katif, Al-Riyadh, Al-Taif, Al-Madina. We collected samples, about 391 respondents and farmers. We also utilized several statistical analysis to minimize and mitigate the errors. We also adopted and utilized a probit analysis. This figure simply describes the users of treated wastewater. As I mentioned, we selected 391 farmers, where 254 of them already use the treated wastewater, while the others don't. As can be seen, that Al-Ahsa Oasis has the highest users of the treated wastewater, followed by Riyadh, Al-Madina, Al-Katif, Al-Madina, and then Al-Taif. This slide shows the farmers' perception about the reuse of the treated wastewater. We have selected several parameters and variables, including the yield productivity, soil fertility, fruits, revenues, cost, water usage, fertilizers, pest, labor, and consumer acceptance. As can be seen, that most of the farmers have responded that there is a positive impact of the reuse of treated wastewater in terms of the soil fertility. For example, they don't need to put a lot of fertilizers, as the treated wastewater is loaded with the nutrients such as nitrogen and phosphorus. As mentioned, the treated wastewater has huge benefits, including the reduction of the reliance on the fresh water, enhance the soil fertility, as well as economic benefits, as the treated wastewater is delivered by the Saudi Irrigation Organization actually for free. Don't need to use any pumps and any equipment. There are some factors affecting the farmers' attitudes towards the treated wastewater. For example, we have positive influences and negative influences, like the satisfaction of the treated wastewater in terms of the quality and the quantity, extension programs provided by the Saudi Irrigation Organization, potential fertilizer savings, and soil improvement. While the negative influences that affected the farmers' attitude is the educational level, as some farmers are non-educated, additional cost impacts, as they think that there is an additional cost they need to add to the farmers while adopting the treated wastewater, and the impact of fruit quality. In order to address the acceptance barrier, we have to reach to the public and discuss more about the importance of shifting towards the treated wastewater quality, and abandon the use or at least reduce the use of groundwater. Also, we need to have to be transparent in terms of the water quality, accessibility of the data. We have also to put some incentives related to the moving to treated wastewater. At the end of this presentation, this study focused on the the awareness of public about the reuse of treated wastewater. Based on the selected farmers, 65% of them already use the treated wastewater. A majority of farmers perceive positive experience on certain aspects like the cost reduction, water usage, and fertilizers. Also, there are some concerns and negative impact on pest, soil quality, and customer acceptance. This study concluded and recommended that we have to invest in infrastructure to expand the use of treated wastewater. We have to develop methods to comply with the water regulation, so whether locally or globally. For example, we have smart monitoring system. We have to combine between the smart monitoring system and the manual system, providing educational courses on the safe use of treated wastewater, conduct workshops and extension programs, as well as putting some incentives and finance. This is the last slide, and this is how we monitor the treated wastewater quality at the Soil Irrigation Organization. We receive the treated wastewater quality from National Water Company. Before we receive the treated wastewater, we check the water quality. We actually check two parameters in the beginning. We check the chlorine, residual chlorine, as well as turbidity. After that, if they are compliant with the KSA regulation, we receive the treated wastewater quality. Then we move to the reservoir. We conduct several parameters and several tests, including physical, microbial, as well as chemical. Including BOD, biochemical oxygen demand, chemical oxygen demand, Legionella, Enterococcus, Pitherococcus, and so on. If it's compliant, also we send it to the farmers for the irrigation. We rechlorinate the treated wastewater in the reservoir to make sure that the water is delivered with high quality. Also, we take some samples from the farmers' outlet to ensure that the water quality within the allowable limit. Again, thank you very much for your attention and highly appreciate your time.
Okay, thank you very much, Dr. Abdurrahman, for a nice presentation. The next presentation will be given by Mrs. Sharifa Bakhaid. Sharifa Bakhaid is a postgraduate professional diploma in teaching from Al-Ain University from United Arab Emirates. She has got Merit Excellent in 2022. She has a Bachelor of Science in Applied Chemistry from Higher College of Technology from Muscat, Oman in 2019. Okay, sorry. Next presentation will be given by Mrs. Sharifa Bakhaid. She is postgraduate professional diploma in teaching from Al-Ain University. She got Merit Excellent in 2022. She has a Bachelor of Science in Applied Chemistry from Higher College of Technology, Muscat, Oman in 2019. She is working as Assistant Instructor, Chemistry, College of Engineering and Technology, University of Technology and Applied Sciences, Salalah. She is lab trainee in Salalah Sanitary Drainage Services. Mrs. Sharifa, floor is yours.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, everybody. Hopefully, all is well. Today, I will talk about the green synthesis of zinc oxide nanoparticles for the waste treatment. Excuse me. It's not. سير ما قبلك الأحمر سوري الأحمر صح لهذا ما قبل أوكي أنا بضغط هذا صح استمع. First of all, I will talk about introduction, experimental green synthesis of zinc oxide nanoparticles, removal of dyes from the wastewater, and I will talk about the conclusion. First of all, I will introduce to you our topic, Zinc oxide nanoparticles are a vertical properties classes of the nanomaterials with a unique physical, chemical, and biological properties. Green synthesis method provide an eco-friendly approach to producing an agent for the formations. It's same problem. Okay. The nanoparticles can be formed using physical and chemical and biological methods. The biological methods can be formed it's an environmentally method considered as the green synthesis. Where it's plant, fungi, bacteria, algae can be formed and can be used as a reducing or capping agent formation. The importance of green synthesis methods, first, it's an environmentally friendly. Green synthesis technique utilize the plant extract, microorganisms, other natural, it's utilize the plant extract, and it can be a natural source avoiding toxic of chemicals and hazardous waste. It's also sustainable production. This method can cost effective, scaled to the industrial manufacturing of zinc oxide nanoparticles. But it's also biocompatibility. Zinc oxide nanoparticles produced improved biocompatibility and making them suitable for biomedical and healthcare application. Now I will talk about the objectives. Our objective, the aim of this objective to synthesis of zinc oxide nanoparticles using Albizia Liebig boats. The following objectives we are in order to reducing and capping the dyes removal from the aqueous solutions. The following objectives we are following to achieve our goal in our project is to collect the plant sample from the Higher College of Technology, Muscat, Oman, then prepare a sample extract using various plant amount, green synthesis of zinc oxide nanoparticles using Albizia Liebig boats, characterize the green synthesis of zinc oxide nanoparticles by using FTIR, SEM, EDX, UV visible, and XRD. Then we will do our applications. The experimental procedure can be explained as the following. We started first by collecting the Albizia Liebig boats from the Higher College of Technology, Muscat, then keep it for 3 days. After that, we are clean it with the distilled water. Then we keep it for 3 days in order to dry. After that, we grounded it into powder. We grounded it into fine powder. We have a different weight of the dry powder. We mix it together in 100 of distilled water, and we heat it at 60 degrees under mixing for 1 hour. After cooling, we have taken 30 ml of the plant extract with 3 grams of zinc oxide nanoparticles with two different temperatures, 60 degrees and 90 degrees, separately. After that, the mixture was heated for 3 hours until the paste was formed. And we can see the yellow And we can see the yellow, the yellow was formed here, the yellow bast. That formation indication of the zinc oxide nanoparticles. Finally, the best yellow was cancelled at 300 Celsius for 2 hours in order to obtain the yellowish white powder named zinc oxide nanoparticles. In the study of the methyl and methyl orange and blue orange, methyl blue. Then we will move to our result. Synthesis and characterization of zinc oxide nanoparticles. The boiled extraction from brown colored solution. The brown colored solution was converted into brown paste. It will convert it into brown paste. Then the calcination, we will do the calcination, and the calcination of the paste produced a light yellow powder. Photochemicals, now we will to move our result. Photochemicals analysis of the prepared zinc oxide nanoparticles must be performed using UV visible and FTIR, which shows the characterization bands and peaks related to the zinc oxide nanoparticles according to the literature. In order to follow the successful preparation, we have conducted a few analyses. Prior application, we started with the FTIR, XRD, and SEM to check, in order to check the crystalline structure, microphology, and chemical composition. We have used XRD, SEM, EDX respectively. So the XRD shows an excellent crystallinity of the zinc oxide nanoparticles as you show here, and it is indicated by the strong diffraction peaks. The SEM shows irregular spherical. Here it's irregular spherical as you see in the picture. Irregular spherical with the rod shape with some agglomeration. And the EDX analysis confirm the successful preparation of the zinc oxide nanoparticles with the zinc 52% of zinc and 24% of oxygen. So the parametric study here, it shows as the prepared nanoparticles was then tested for the catalyst degradation of the methyl and orange, methyl blue and methyl orange dyes. The influence of the nanoparticles temperature preparation on the dyes degradation show that the removal of orange, methyl orange, and blue methyl, it's shown as here. Then we get the influence of the nanoparticles temperature, preparation of the dye degradation, and it shows the methyl orange, it's the best one. So to sum about our topic, the green synthesis of zinc oxide nanoparticles present a sustainable and effective of approach to remove the dye removal from the wastewater, and it is an eco-environmentally process for the green synthesis of zinc oxide nanoparticles, and the Albizia lipic boats extract possess some photochemicals which not only perform in the reduction of the participate size, but also its provide stabilization and methyl blue and methyl orange degradation efficiently synthesis the nanoparticles reached 48 and 87% respectively. Thank you so much, and that's it.
Thank you very much, Mrs. Sharifa, for the interesting presentation. The next presentation, before I invite Mr. Ahmed Al-Faqi and Dr. Amal. Ahmed Al-Faqi and Dr. Amal.
No.
Allah. Alaikum assalam wa barakatuh. Okay, fine. Welcome, Dr. Mr. Ahmed Al-Faqi. Actually, Ahmed Al-Faqi works as a researcher at King Saud University. He earned his MSc from the same university since March 2019. He is conducting research on water conservation techniques such as deficit irrigation and agricultural water resources management. He worked on different projects in water resources management such as water reuse and rainwater harvesting and hydrological modeling. He holds his bachelor's degree from the Agricultural Sciences College of Kafr Sheikh, University, Egypt. His master's degree was obtained in agricultural engineering from King Saud University since March 2019. Actually, he is a PhD student at King Saud University. His thesis titled is maximizing the use of treated wastewater through integration between geographic information systems and multi-criteria decision-maker analysis. Mr. Ahmed, floor is yours.
Thank you very much.
You have 15 minutes, okay?
Can you listen me? Yes.
Okay.
Can I share my screen? Sorry. Hello, everyone. My screen. My screen is visible.
We see
you?
it. Yeah. We see your screen.
Assalamu alaikum wa rahmatullahi wa barakatuh. Hello, everyone. Thank you very much for the audience. Thank you for the Water Science Technology Association. Today I will talk about comparative wastewater quality indicators and multivariate analysis of Riyadh sewage treatment plants and its impact on irrigation of Riyadh district. I am Ahmed Al-Faqi. I am a PhD student in King Saud University. This paper by me and Dr. Ahmed Al-Shafi and Dr. Faisal from King Saud University. Today, in the beginning, what is a challenge of ours, and what do we dream, or what has been achieved, what do we dream of achieving? The challenge in beginning, there are 18 million trees. Sorry. There are 18 million trees have been planted in Saudi Arabia in the green project, and the dream is to plant 600 million trees. The challenge is Saudi Arabia faces a shortage of annual water due to its extensive afforestation initiative and the need to irrigate 10 billion trees. As we know from statistics, treated wastewater use in agriculture in KSA equal 400 million, almost 37.6% of treated wastewater. But in Riyadh, our case study, just 41 41 million cubic meters, or 7.5%, is used for agriculture, with the amount of wastewater in Riyadh. The total capacity of 133 wastewater treatment plants in the Kingdom of Saudi Arabia is 1.87 billion cubic meters. This amount can cover 220% of the gap between water demand and supply in the agricultural field. According to the 2030 Saudi Vision, Saudi Arabia aspire to entirely reuse 100 of treated wastewater. The importance of the study: treated wastewater is available all year and contain nutrients required for agricultural growth, so it can used as a source throughout the year. Treated wastewater might be a component of the solution to supply the water needed from this green Riyadh project. So it is necessary to confirm the source's quality before using it for irrigation. Our study assessed the water quality, pollution, and suitability for irrigation by analyzing historical treated wastewater data from wastewater treatment plants in Riyadh city. The objectives, there are 4 objectives. The first objective: to examine the temporal variation of treated wastewater parameters, as well as the key factors affecting treated wastewater quality. The second objective: to ascertain if treated wastewater is suitable for irrigation. The third: to comprehend the statistical relationship between parameters. The fourth objective is to explain how the factors related to wastewater quality affect, explain how the factors related to wastewater quality affect the parameters, and show how to reduce the redundant variable by using principal component analysis. Methodology: in the beginning, our case study is Riyadh. Riyadh is the capital of Saudi Arabia. Its population is 7.5 million, almost 25% of the total population of Kingdom of Saudi Arabia. Riyadh is divided into 4 populated areas: east, north, south. Riyadh, Manfuha, and Heat, and Al Hayr, as described in details in this table. The treated wastewater quality parameters, as we show, we collected for 4 years the data from the Ministry of Agriculture and Water for 13 parameters, and all sampling and analytical techniques were carried following the American Public Health Association. This is treated wastewater quality parameter data. We have chemical oxygen demand and microbiological analysis, E. coli, and ammonia and NO3 turbidity and EC and pH and dissolved oxygen. The water quality indexes. There are 21 different water quality models, such as Horton and Oregon Index and British Columbia and Canadian Council of Ministers of the Environment Index. We select which is the Canadian Water Quality Index because it depends a lot of parameters. And this is the equation for Canadian wastewater quality indexes. The categories or ranking of Canadian water quality indexes, there are 5 categories from poor to excellent, from 0 to 100%. The second index is Comprehensive Pollution Index, which calculated by dividing a measured concentration of individual parameter by standard permissible concentration of parameters. The multivariate analysis, such as principal component analysis, was utilized for understanding the key factors of water quality parameters, BCA can decrease the number of input variables in order to create reliable and sample prediction models to correlate target variable. We conduct this statistical analysis by using XLStat program. The result, the classification of treated wastewater parameters samples from Riyadh treated wastewater plants over 4 years based on the standard limit. We find that the data of SAR, NA, CMG, TDS, and ECBH were all below the maximum permitted limit. However, 18 of COD and 29 of NO3 and 39 of NH4 were exceeded the maximum permitted limit. Also, 56% of turbidity were exceeded the permitted limit. This may be due to the insufficient wastewater treatment, but the reuse of treated wastewater, particularly for irrigated crops, doesn't pose significant health risk. The result of comprehensive pollution index, it was found that comprehensive pollution index for ranged from 0.42 to 1.39. This quality is slightly polluted as categories of comprehensive pollution index. So there is no significant public health associated with the reuse of treated wastewater, especially for irrigated crops. The Canadian water quality indexes, it ranged between 73 and 95. Almost 18% of samples fall into fair category. However, 75% of the samples were in good categories. The principal component analysis, this table shows the eigenvalue of 5 components, F1 to F5. The first primary component in the data set account for 18% of the total variability in the data, and this component is the most important because it can provide a dominant pattern of data set to understanding treated wastewater quality parameters. It accounts parameter loading of CAMG, EC, NO3, and turbidity. The second component accounts for 12.7% of the data variation, which including NH4, COD, and DO. To predict the Canadian Water Quality Index, we developed a stepwise regression model with model 5, which include 2 parameters, is the least variable. It have a least variable, but the best model is model 1 because the coefficient of determination and the coefficient of variation is highest, and the mean square error is the lowest. This is the Canadian Water Quality Index's equation obtained from the 5 models. There are a strong correlation between NO3, turbidity, and Canadian Water Quality Indexes. Conclusion, TDS, pH, and free chlorine, and SCR, NA, DO, and CMG parameter didn't exceeded the maximum levels allowed for restricted irrigation, the average comprehensive pollution index value ranged from 0.42 to 1.39, indicating slightly pollution throughout the study period. The Canadian Water Quality Index is ranged between 73 to 95, indicating the use of treated wastewater couldn't harm public health, especially for irrigated crops. The principal component analysis of wastewater dataset reveals that the first component accounting for 18% of total information, which include ACCA turbidity parameters. And the second component exists in NH4, COD, and DO. The study found a strong correlation between turbidity, nitrates, and Canadian water quality indexes. A stepwise regression model was used to predict Canadian water quality index, with model 5 have fewest variables, 2 variables. However, model 1 was the best with 7 variables. The result may also benefit farming methods that preserve soil health and water sustainability. This is the practical implication of finding. The outcome of this study have potential to improve the environment and welfare of community by establishing evidence-based regulation for wastewater management. The finding can guide the development of evidence-based policies and recommendation of agriculture and wastewater management in Riyadh, aiding in monitoring plans and water quality goals. Understanding current trends and potential future changes can also aid in long-term initiatives like infrastructure development and land use planning. Policymakers may utilize the study conclusion to direct funding toward the implementing of pollution control and program monitoring and support sustainable production. Thank you very much.
Thank you very much, Mr. Ahmed. We have the last presentation that will be given by Dr. Amal. Also, it will be virtual. Dr. Amal.
Assalamu alaikum. I have one question for Dr. Jamal regarding the multi-treatment for the wastewater using the biodegradation and electrocoagulation and the membrane as well. Putting all the techniques in the same at the same time, it's very, very challenging. Actually, at the University of Technology and Applied Sciences, we have started this project with the collaboration of the Oman Water and Wastewater Service Company, and we selected the stage at which we will implement the electrocoagulation, and this is a one-year project that will be scaled up, and the results are really promises as a stage to do the treatment before going to the membrane, which will increase the shelf life of the membrane. But we have not tried the biodegradation because the company has its own way of doing this part. We did the electrocoagulation then before going to the membrane. So this is my recommendation for this project.
Thank you, Doctor, for your comments. Actually, I applied both alternatives. In Canada, actually, we invited this technology in Montreal. We integrated all these processes in one reactor vessel, as you know from the presentation. And then later on, we found maybe better to keep the microorganism survival for a long time, to apply pre-treatment electrocoagulation. We did that also in American University in Cairo in 2012. I have many publications in this regard. Now we have to compare between, to isolate the electrocoagulation from membrane filtration or to integrate all them together. As I mentioned in my presentation, we have challenge actually to keep the surveillance for the microorganism for life. So we have to select the best kinetics in terms of electrical kinetics, in terms of DC, in terms of the operation mode, on-off. You know, you have to apply the direct current intervally on-off to keep the microorganism survive for a long time. I agree with you, maybe the external may be better, but our technology actually has many benefits, as I mentioned in my presentation. And also for Oman, I applied also a collaboration research with Sultan Qaboos. We applied last month between Qatar University and Sultan Qaboos University, and we need to apply this technology on hydroponic wastewater treatment. Thank you.
Next question. تفضل.
Thank you. Thank you. Thank all speakers, including the one who was vital. Actually, my question is two parts. I think the only one who answered my second question was Dr. Khalid, and that was then recommending go to a pilot plant. So I think that should have been part of the conclusion of every one of those papers. What would be the next step? Going to pilot plant or going to commercialization? I'd like to have an answer from all speakers.
Yes, I thought this is one of my recommendations at the end of the presentation. Actually, as I heard from my professor in Canada, they start to find a collaborative with industry. We need, you know, this is very expensive research, and we need some company to take the challenge to apply this on the field, actually. But we applied, pilot scale, we applied in Concordia. My colleagues after me, we have 4 researchers. They applied the pilot scale on Concordia.
Okay, Dr. Amal. Okay, go ahead, Dr.
Sorry for interrupt. Yes, we did that, and we have 2 publications for pilot, but still there is a challenge, as the doctor mentioned, in applying the electrokinetics on the microorganism. This is a big challenge in our technology. I agree with you, yes.
It's easy to find a sponsor for a pilot plant. Not commercial plant is something else. And even the commercial will not come to you before you show them the pilot.
Yes.
The pilot will be an encouragement, an incentive for the commercial.
Yes. Actually, I will start my research in this issue, and because I have here in Qatar University for 2 years, and I applied for the research for QRDI this year, and we hope we can get sponsorship from this grant to modify our technology, inshallah, here in Qatar, because here is the best location in Gulf area, because we can use the solar energy for this technology.
Okay, Dr. Amal.
ايوه السلام عليكم.
وعليكم السلام ورحمة الله وبركاته. Okay.
سوري اخرتكم بس صارت مشكلة عندي.
Okay, no problem. I'm going to introduce you, then you can give your presentation, okay?
Okay, إن شاء الله.
Okay, Dr. Amal has a PhD in Chemical and Process Engineering from University of Leeds, UK. She is one of the experts in Oman and Gulf region in waste-to-energy technology. She is at present a lecturer at chemistry department at University of Technology and Applied Sciences in the Oman. Dr. Amal has presented many researches for peer review at conferences in Munich, Germany, Austria, France, Spain, and Greece. She is preparing more research materials for forthcoming international conferences in her field of study. Conversion of waste materials to value-added products such as hydrogen, syngas, and carbon. Dr. Amal, floor is yours, please.
السلام عليكم ورحمة الله وبركاته. أول شيء أعتذر عن التأخير. So this is Dr. Amal Al-Rahbi from University of Technology and Applied Sciences. And today here, I am here today to present the results related to using a low-cost adsorbent for an efficient removal of heavy metals from aqueous solution.
Sorry, Dr. Amal, you have 15 minutes, okay?
Inshallah. So in today's presentation, I'll give a short introduction about the project, and then I'll present the methodology followed in this project and the results obtained, and finally a short conclusion. In introduction, as it is presented here in this figure, that we have different global issues faced by different regions. So for example, in Asia, there are two major concerns, which are the food waste and plastic waste. And these two types of waste, or waste in general, it should be managed properly. If this type of waste is not managed properly, definitely it will be a source of greenhouse gases emissions. So as it is presented here in this figure, if you see, according to the statistics, around 3.2% of greenhouse gases are emitted from waste, and about 1.9% is coming from landfills. So in order to manage these types of waste, this waste has to be diverted away from landfills and should be managed before it reaches the landfills. The project will be focused only in fruit waste. Okay, we have different types of fruit waste, for example, peels, seeds, stones, and hulls. This waste, there is an issue with the disposal or recycling of these types of waste. However, the good thing about this type of waste that it has different functional groups, for example, carboxylic acids and hydroxyl. These functional groups, it acts as active sites for the removal of heavy metals and for the removal of contaminants from wastewater. So as I mentioned before, we have different types of waste generated from wood industry, farming, and fishing industry. In order to manage this type of waste and for the waste management, this type of waste can be converted as to biosorbent, adsorbent, okay, by using different methods, for example, pyrolysis, anaerobic digestion, composting, recycling. Later on, it can be used as adsorbent to remove heavy metals or to treat contaminated water. So different mechanisms involved during the adsorption process or the biosorption process. The aim of this project is to understand what is going on during the removal of heavy metals by using adsorbent. So as it is shows here in this figure, we have different steps, okay? And this is the structure of the material. The first step involves in the removal of heavy metals is by removing of the contaminants from the aqueous solution to the first layer of the adsorbent. The second step is the diffusion of these heavy metals into the pores of the using adsorbent, and finally there will be this adsorbent will form will form a bond with the used functional groups. Different process or different mechanisms will happen during the removal of heavy metals. There is ion exchange or co-precipitation, oxidation, reduction. However, this project will be focused only in physical adsorption as it is the easiest one. So let us move now to the methodology part. So the methodology part involves the using of the raw material. Just I need to mention that actually this project we have focused in two main issues faced by UTAS. One of the issues that we have a huge amount of banana peels in restaurants, okay, and also we have another issue in lab, which is the industrial wastewater. Okay, so what we have done, we have converted the banana peels into into a material, into biosorbent material, and this biosorbent material can be used later to treat the wastewater produced in laboratories. Okay, so for the adsorbent preparation, the banana peels were directly used. Only it has been treated by phosphoric acid and methanol treatment. Methanol treatment was done for the esterification process, and we have used two types of acids. This is in order to find out the responsible functional groups for the removal of heavy metals. So two types of acids were used to modify the functional groups in the used adsorbent material. Later on, as I mentioned before, the adsorbent were used to treat the wastewater generated in laboratories. Okay, for the removal of heavy metal, lead and nickel were used as heavy metals. Different parameters were used or were studied, the influence of pH and the influence of dosage, and also influence of time and influence of concentration. And this is only to just study the kinetics of the removal of heavy metals. So let me just present the results. So if you see this figure, it shows the FTIR of the raw material and the one treated with methanol and the one treated with phosphoric acid. Okay, if you see here in this figure, it shows that there is a reduction in the hydroxyl groups, okay? And some of the functional groups have been reduced, and also the spectra, it shows that there are significant amounts of acidic oxygen containing functional groups such as carboxyl and hydroxyl, and definitely these types of functional groups will have a significant role in enhancing the metal removal. Okay, if we see the SEM, the morphology of the prepared materials, okay, there is a little bit different between the used one, the raw one, and the methanol treated one. Okay, the good thing about the one treated with phosphoric acid is it generates a porous material, and these porous materials definitely will have a role in enhancing the metals removal, and as we will see in the coming results. So as I mentioned before, that we have different parameters. The first parameter is the influence of pH. The pH has an impact on the overall charge of the used adsorbent and also the solubility of metal ions. For this reason, the influence of pH was studied, and the maximum removal of lead was around 80% and was obtained by the material prepared or treated by phosphoric acid, while for nickel, the maximum was around 42%, and again with the material treated with the phosphoric acid. Again, the time also was studied, the influence of time, okay, for both, for lead and nickel, okay, 87% for the one treated with phosphoric acid, and around 45% with the one treated with phosphoric acid as well. The influence of dosage as well was studied in order to find out the optimum one, okay? And the optimum one for both metals was around 3 grams. 82% was obtained with lead, and 50% was obtained with nickel with the use of 3 grams. The influence of concentration was examined as well to investigate the variation of removal efficiency with the initial concentration. As it is presented here in the figures, that the removal efficiency has increased with the increase of metals ion concentration from 10 to 40 ppm. And the sample treated with phosphoric acid had the maximum metals removal. 82% with the phosphoric acid and 45% as well with the sample treated with phosphoric acid. Okay, so different parameters were studied, and this is in order to understand the kinetic, or in order to understand the mechanism happened during the removal of heavy metals. For the kinetic study, For the kinetic study, both the results for lead and for nickel, okay, they have followed Langmuir isotherm model, which means that the adsorption or the removal, it happened in a monomolecular layer on the adsorbent surface. However, for the nickel, it followed Freundlich isotherm model, okay, which means that the surface is extremely heterogeneous. So in order to apply the used biosorbents, it can be applied for effluent polishing. Okay, it can be used as a final step to remove the trace heavy metals from treated water. So it can be used in our laboratories as well before we send the wastewater for treatment. And also it can be used for continuous treatment, where it can be used in a fixed bed reactor. It can be used as well for sludge stabilization. However, there are different challenges we need to consider before we use this technology. As I mentioned before, that this is only a lab scale study. So in order to implement this study, different challenges has to be considered. The first one is the scalability. We need to develop a cost-effective, large-scale biosorption systems, and this remains the key challenge faced by most of the wastewater treatment industries. The second one is the regeneration. The efficient methods for desorbing and regenerating spent biosorbents needs further research. The last one is the selectivity. We need to improve the selectivity of the used biosorbents for the specific heavy metals. In conclusion, the banana peels has been treated with methanol and phosphoric acid to understand the main mechanism going on during the removal of heavy metals. The material treated with phosphoric acid, it had the highest lead removal, where about 84% of removal has been obtained with the use of 4 gram and at pH 6. Biosorbents offer a sustainable and cost-effective solution for water purification. And thank you.
Thank you very much, Dr. Amal, for an interesting presentation.
Thank you.
Actually, we have exceeded the time, but we are going to give a chance for 1 or 2 questions maximum.
She answered my question.
Fine. Any more questions?
No more.
Okay, thank you very much. Thank you very much for the presenters. And we are going to close the session. And maybe the time is for lunch, or let me ask Dr. Walid if he has anything to say.